Hello, my name is Kaylin, and this is my Lab4 presentation on the magnetic field of a bar magnet. In this lab, I explored how the strength of a bar magnet's field changes with distance and compared my experimental results to my theoretical dipole model. The goal of this experiment was to measure how the magnetic field strength varies along the magnet's axis and to calculate the magnetic dipole moment. We applied magnetic dipole theory to the model to model the field behavior and compare our observations with theory. The results showed that the field decreases roughly as 1 over r squared rather than the expected 1 over r cubed, with a dipole moment of about 24 amp square meters. So for the key equations, I used the main theory behind this lab, which is magnetic dipole model, where the magnetic field is given by the equation B B equals mu naught over 4 pi times r cubed times 3 mu times r hat times r hat minus mu. And then along the axis of the negative field, that we use a simplified version of bx is equal to mu naught over 2 pi times m over r cubed. And then we use power law, which is ln times bx, which is equal to n ln times r plus ln c. And then lastly, we use the magnetic dipole moment m equals 2 pi c divided by mu naught. And then for the experimental setup, I use a magnetometer on my phone to record the magnetic field at different distances from the bar magnet. The data was entered into an Excel to plot the ln bx versus ln r. And then before measuring, I aligned the phone with magnetic north to cancel Earth's electric field and isolate the magnet's contribution. So the magnetometer's readings were taken at multiple distances along the magnetic axis. Each measurement was repeated to reduce random error and average before plotting. The resulting data produced a clear downward trend showing that the magnetic field weakens with distance. So for the results, the experimental plot of lnbx versus lnr produced a slope of negative 1.95 and an intercept of negative 12.253. From the intercept, we found that the proportionality constant C equals 4.78 times 10 to the negative 6. And then using this value, we calculated the magnetic dipole moment to be approximately 24 amp meters squared. So for the observations, the slope of negative 9.5 indicates that the field decreases more slowly than the theoretical -3 slope, as expected. The field strength increases significantly as the magnetometer was moved closer to the magnet. Overall, the results confirm that the magnetic field weakens with increasing distance from the source. To visualize the magnetic field, I use GlowScript v Python simulation. I entered my experimental magnetic dipole moment of 24 amperes meters squared into the code, and it generated a 3D field arrow showing the direction and relative strengths of the magnetic field along the perpendicular of the magnetic axis. So first, some assumptions and errors. We assume that the magnet behaved as an ideal dipole with uniform magnetization and negligible interference from Earth's field. Possible sources of error include environmental magnetic noise, small alignment errors, and sensor inaccuracies from the phone's magnetometer. These factors likely contributed to the slope being slightly less steep than the theoretical -3. So for the what if questions, the first one, how would results change if the meter stick was alternated in different rotations? If I hadn't aligned the setup with magnetic north and the Earth's field would have added or subtracted from the magnetic field, causing inaccurate Bx values and an incorrect dipole moment. And then for the second one, and so going back to the first one, the overall data would be inconsistent, leading to an incorrect slope and magnetic moment. And then for the second question, how would measurements differ if you had two identical magnets? This would double the total magnetic dipole moment, so the measured magnetic field would be twice at every point. However, the same inverse distance relationship since the dipole geometry is the same. And yeah, that's it for my lab. Thank you so much for listening.